In this session, we consider functions of random variables, which would also be random variables. And we've already done a little bit about this. For example, we considered random variables x and their expectations. And then when we wanted the variance, we considered the random variable x squared and its expectation, right? We needed that to calculate the variance. So here we consider general functions of random variables. So an example, we flip a fair coin. The random variable x takes the value 1 if the result is heads, -1 if the result is tails. Okay, so that's a random variable. What's the PMF for x? If we assume a fair coin, then the probability is 1/2 for x to be equal to +1, that is to get a head, and 1/2 for x to be equal to -1, that is for us to get a tail, and the probability is 0 for any other value of the random variable. Okay, let's define a second random variable, y equals x squared. What's the PMF for y? Well, if x squared, x can take values +1 or -1, then x squared takes values +1. So f sub y of y takes the value 1 for y is equal to 1, and then takes the value 0 for anything else. Okay, so that's an example of y equals x squared is the example of a function of a random variable. And we can find, if we know the PMF for, or the PDF for x, then we can find we try to find the PMF or the PDF for y is equal to some function of x. Okay. Now, how about this one? We have a random variable x. It takes values 1, 2, 3, and so on. And it takes these values with the probability 3/4, 1/4 to the x minus 1 for the allowed values of x. And for the non-allowed values of x, the probability is set equal to 0. Now let's say that y is equal to x squared. How would we find the PMF for y? Well, y would take values 1 squared, 2 squared, 3 squared, and 4 squared. And if it takes the value of x squared, then it takes that value with the that means that if y takes the value x squared, then x took the value x, and the probability to get that value of x is given by this PMF. So now we can say this. This is how we write that. That if p of y is equal to n squared, what does that imply? That if y equals n squared implies that x is equal to n. So the probability that y equals n squared is the probability that x is equal to n. And then the allowed values of n for x, the allowed values of x, these were 1, 2, 3, and so on, and 0 for anything else. Right? So then f sub y of n would equal f sub y of n squared would equal 3/4, 1/4, n minus 1, right? And then f sub n of y would equal 3/4, 1/4, and then what is x in terms of y? X in terms of y is the square root. So square root of y minus 1 for y equals 1 squared, 2 squared, 3 squared, and 0 otherwise. Okay. Now, when the function is 1-to-1, we can figuring out the PMF is a particular form. So we consider that that's a special case. I should remind you what 1-to-1 means. So 1-to-1 or injective. Function is 1-to-1 if f of a equals f of b implies that a is equal to b. So for example, if f sends reals to reals is defined by f of x equals x cubed, that function is 1-to-1. If f of x equals f of y, that is y cubed is equal to x cubed, then it implies that y is equal to x. Okay, f sends integers to integers defined by f of x equals x squared is not 1-to-1. Why? Because f of -1 is also equal to f of 1 is equal to 1. So -1 squared is the same as +1 squared. So 2 points in the domain can be mapped to 1 point in the range. So the function is not 1-to-1. Okay. On the other hand, if you're mapping from the positive integers to the positive integers, f of x equals x squared, then if f of a equals f of b, a squared is equal to b squared, then in fact a is equal to b because we're only talking about positive integers. Okay, so here's the idea. If f is 1-to-1, then that fact can be used to find the PMF of x. Basically, you're going to be looking at the inverse of f to do this. So if supposing that some map u is 1-to-1, x is a discrete random variable which has a PMF f sub x, let the new random variable y equal u of x, and that's a 1-to-1 transformation between the values of x and y. Then it means that y equals u of x can be solved for x by x is equal to v of y. V would be the inverse of u, right? So then f sub y of y is equal to f sub x of v of y. Okay, we've already seen this. So f sub x of x equals 3/4, 1/4 to the x minus 1 for x equals 1, 2, 3, and so on. Now, what's f sub x of y? Well, the values of y would be equal to 1 squared, 2 squared, and 3 squared. And they appear with the probability 3/4, 1/4, x to the minus 1. The x is defined because u is 1-to-1. And usually when we write y is equal to x squared, then we can write x is equal to square root of y, not plus or minus square root of y because this is 1-to-1. Okay, so then you could replace this x by root of y. Okay, so that's what we've done over here. So in the 1-to-1 case for discrete random variables, it's fairly easy. Okay, let's try another one. Consider x with f sub x defined by f sub x of k is equal to lambda the k e to the minus lambda over k factorial, and k is equal to 0, 1, 2, 3, and so on, and 0 otherwise. Define a random variable y equals 3x. Is multiplying by 3 1-to-1? Well, yes, it is, right? If 3a is equal to 3b, then that implies that a is equal to b. So then f sub y of y, right? So what's k? K would be equal to y over 3. So you replace k by y over 3. And over here, if k is taking values 0, 1, 2, 3, then y is taking values 0, 3, 6, 9. Okay. So we have e to the negative lambda y, lambda to the k. Well, k is equal to y over 3, divided by k factorial, while k is equal to y over 3. And k is taking values 0, 1, 2, 3, and so y is taking values 3 times 0, 3 times 1, 3 times 2, 3 times 2, and so on. And otherwise, no other values occur. All right. Now, suppose x has a function defined like this. F sub x of x is equal to 1/3 for x equals -1, 0, and 1. It's 0 otherwise. And y is equal to 2x minus 1. So what values can that have? 2 times -1 minus 1, 2 times 0 minus 1, and 2 times 1 minus 1. Okay, and x in terms of y is y plus 1 over 2. So that transformation is also 1-to-1. X is equal to y plus 1 over 2. Then what are the allowed values of y? Well, if the allowed values of x are -1, 0, and 1, then the values that y take are -3, -1, and 1. So the corresponding value of x occurs with probability 1/3. So the corresponding value of y occurs with probability 1/3 and 0 otherwise. Okay, so those were some random variable, some transformations of random variables, and how to find their PMFs given that the transformation from the original random variable to the transformed one is 1-to-1. And now we consider the continuous case. Okay. So again, let's consider 1-to-1 transformations. So there's a 1-to-1 transformation, and we will have an inverse. So if y equals u of x, then x is equal to some v of y, where v is the transform, where v is the inverse of u. Now it looks a little bit different. F sub y of y is equal to f sub x of v of y, right? Basically f sub x of x, which is equal to v of y. And here you have to multiply by the absolute value of the derivative of the inverse function, v of y. Okay, so that's the difference. So f sub x of x is equal to 2x as x goes, when x takes values between 0 and 1, and it's 0 otherwise. So let's say we've checked that that's a PDF. So what's the PDF for y is equal to 2x minus 3? Well, okay, so we transform this value twice x is occurring for 0 goes from x goes from 0 to 1. Well, if x goes from 0 to 1, then y varies between -3 and -1. So y is going to, this would be replaced by y going between -3 and -1. And what's 2x? 2x is y minus 3. So 2x will be replaced by y minus 3, except that, remember, you also have to multiply by the absolute value of the derivative. So work out what the inverse function is, and then we'll see. Okay, so the transformation is defined by u of x equals 2x minus 3. That is 1-to-1. Then x is equal to y plus 3 over 2. So that's a transformation of y. That's the v that we're looking for. Its derivative with respect to y is 1/2, right? So v of y is 1/2 y plus 3, and the derivative of that, and then you take its absolute value, is 1/2. So v of y times the derivative of v is 1/2 y plus 3 times 1/2. Sorry, times the absolute value of the derivative of y. So that should be absolute value of 1/2, which is 1/2. And that's equal to y plus 3 over 4. So the PDF is going to be S of y is equal to y plus 3 over 4. Y would be varying between -3 and -1. And then the 0 doesn't change. Okay. And you need to specify, in order to specify a function fully, you have to specify its domain fully. So be sure to put this business in here. -3 is less than 1, so it's -1. Okay, so that's one way to do it. Another way is this. I have the PDF maybe of the original random variable. Instead of finding the PDF of the transformed random variable, find the cumulative distribution function first, and then take its derivative to find the PDF of the transformed random variable. So let's try that. Okay, so x has a PDF f sub x. It has a CDF capital F sub x. And y is equal to some transform g of x. And it has some CDF capital F sub y and some PDF f sub y. We want to find the PDF f sub y. We find the CDF f sub y first, and then take its derivative to find the PDF f sub y. Okay. Remember what the cumulative distribution was. The cumulative distribution is the probability that y takes values. F sub y of y is the probability that y takes values less than or equal to y. So that's the integral from -infinity to y of the PDF. So I can find the PDF by differentiate. If I can find this first, the cumulative CDF first, then I can take its derivative to find the PDF. Okay. Now, f sub y of y is the probability that y is less than or equal to y. But what was y? Y was some g of x. So f sub y of y is the probability that g of x is less than or equal to y. So f sub y of y is equal to the integral over the values of x such that g of x is less than or equal to y times the PDF of x for x evaluated at s ds. Okay, then having found the CDF of y, one can differentiate the CDF to find the PDF. Okay, so let's try an example. We have the uniform distribution on 0 to 1. Okay, that's my function. So x takes values from 0 to 1. And that would be some constant on the interval from 0 to 1. And it would be 0 otherwise. And y is equal to the exponential of x, that's a transform variable. So the PDF, not the PMF, sorry. The PDF for x is defined by f sub x of x is equal to 1 for x an element from 0 to 1, and it's 0 otherwise. That's the PDF for the continuous uniformly distributed random variable on the unit interval. Now, the CDF is for things, for values of x less than 0, the CDF for x looks like this. It's 0 for values less than 0. If you integrate 1, you get x. So it's x from 0 goes from x to 1. And it will be 1 for x bigger than 0, because there's a probability of 1 that it takes values less than 1. Right? Okay. So then the values that, so if x can take values 0 to 1, then what values can the exponential of x take? Well, they can take values from 1 to e, right? So when you specify your CDF and your PDF for y, you have to know what the range of y is, right? You have to know what values y can take. It takes no other values. So the probability, the CDF, f sub y of y, is the probability that capital Y is less than or equal to small y. But what was capital Y? It was the exponential of x. So it's the probability the exponential of x is less than or equal to 1. Okay, well, this is a nice one-to-one function. It has an inverse, which is the logarithm. So that's the probability that x is less than or equal to the log of y, right? So what's the probability that x is equal to less than or equal to y over y? It's the CDF for x evaluated at the log of y. Okay. So that is, we come back here. So that's 0 for x is less than 0. X, this is for x, but if I replace x by log of x, by log of y, so that's 0 for, what's x? It's log of y is less than 0. This is, replace x is the same as log of y. So this is log of y for 0 less than or equal to log of y less than or equal to 1. And it's 1 for log of y bigger than 1, which is, what's that in terms of y? Think about that for a second. Okay. So it's 0 for log of y less than 0. It's log of y for 0 less than or equal to log of y less than 1. It's 1 for log of y greater than 1, or for y greater than e. Here, y is, log of y is varying between 1 and e, right? So f sub y of y is equal to 0. Okay, so now to find the PDF from the CDF. This is the CDF for y. We have to take the derivative with respect to y. So we get 0 for log of y less than 0. Derivative of log of y is 1 over y for 1 less than or equal to y less than or equal to e. Right? E to the 0 is 1, and e to the 1 is e. And this derivative is 0 for log of y bigger than 1 is the same as y is bigger than e. And you have it. Okay. So for the continuous case, there might be two ways that you can think of doing the problem. One is to, if the transformation is 1-to-1, one way to do it is to use the formula f sub y of y is equal to you transform in terms of x's, you write them in terms of y's, and then you have to multiply by the absolute value of the derivative of the transform. The other way, which will be easier in many cases, is to find the CDF for y first, and then take its derivative to find the PDF for y.